This audiovisual program is to help understand the block diagram and the operation of JVC GX-V7 color video camera. First, we start with the block diagram of the video process system. This is the diagram of the video process system. The color multiple signal from the Vidicon is amplified by a high SN preamplifier. Then, the pre-process amplifier takes over to compensate its dark current, to compress its peak, to do AGC, to compensate its burning, and to correct its phase. The pre-process output is guided to the Y process amplifier, the R and B separation and G separation units. The Y process amplifier does the signal molding by compensating the aperture, by doing white clip, by mixing the blanking signal, and by establishing the Y setup signal. Its output is held to the encoder. The G-signal separationer is the mechanism to take out the low-frequency component, that is, the G-signal, from the color multiplex signal. The low-pass filter only allows the low-frequency component of the color multiplex signal to go through, and its output signal is G plus 2/3 B and 1/3 R. Then, the G matrix waits to cancel its unnecessary B and R components of the low-pass filter output and to produce the pure G signal. This cancellation is done by detecting R and B and feeding the reverse phase R and B signals back to the G matrix. The color multiplex signal guided to the R and B separationer first goes through the peak white balance compensation to improve the highlight part of it. Then the 4.1 MHz and 8.2 MHz band pass filters extract the R and B carrier waves. That is, 4.1 MHz fundamental wave and 8.2 MHz secondary higher harmonic. This extracted secondary higher harmonic furthermore takes a sufficient amplitude limitation from the limiter and goes to the multiplier. The multiplier executes the multiplication of 4.1 MHz fundamental and 8.2 MHz higher harmonic. This way, the secondary higher harmonic is converted to 4.1 MHz. This new 4.1 MHz wave makes the B signal amplitude modulation wave by adding the original 4.1 MHz fundamental and the R signal AM wave by subtracting the original fundamental wave. This AM wave, amplitude modulated according to the intensity of light, is detected by the following synchronous detection circuit to produce the R and B primary color image signals according to their amplitude. From R channel to B channel, through the B matrix potentiometer, the R signal is added to eliminate the R signal disturbance on the B channel so that the better color reproducibility is expected. The R and B primary color image signals go through the electronic attenuator circuits, which corrects their color temperatures. Then they are guided to the color difference matrix circuit to be matrixed with G signal. Here, according to NTSC standard, the R-Y and Y-B color difference signals result. These signals are to be reproduced DC-wise and are heading for the encoders. This is almost it about the video process block diagram. We are now going into details of the flow of signal and the operation in the video process system following this diagram. So please be familiar with this diagram very well. Preamplifier. The preamplifier is the system to boost up the delicate signal from the camera tube to make the signal processing job in the following circuits easier. The most important thing about the preamplifier is signal-to-noise ratio, because it amplifies the delicate signal from the Vidicon. So practically, this preamplifier's SN ratio is the determinant of that of the whole camera system. Therefore, many features to improve the SN ratio are found in this circuit. For example, the top FETs are connected in parallel to increase apparent GM. The Percival circuit is inserted at the preamplifier input. The negative feedback is given to the top to lower the input impedance. Here is the preamplifier block diagram. The signal from the Vidicon through Percival coil is guided to the preamplifier circuit. The Percival coil resonates in 8.2 MHz with the output capacitance of the Vidicon and the preamplifier's equivalent input capacitance. This improves the SN at 8.2 MHz by about 5 decibels. Furthermore, the preamplifier's input gate gets a feedback from its output. This reduces its input impedance and improves its frequency characteristic and its SN. Now, let's look at the actual preamplifier circuit. L101 is the Percival coil. The input circuit of the preamplifier consists of a parallel connected FETs to enhance the apparent GM for better SN. The negative feedback is given from the preamplifier's output through R114, C107, and R104 to the top FET's gate. The signal runs through L101, X102, X103, X101, X104, X105, X106, X107, and goes out for the next preprocessor. Preprocessor. The color multiplex signal boosted to around 0.3 volts is put through the steps of dark current compensation, burning compensation, peak compensation, AGC, and color phase compensation in the preprocess amplifier. First of all, let's discuss the dark current compensation circuit. The rise in the Vidicon's target phase temperature brings about the dark current increase. This increase in dark current fluctuates the setup levels of the lower component of the signal, that is, those of the luminance signal and the green signal. This causes the greeny picture reproduction, so the dark current compensator is the mechanism to stabilize the black level against the dark current fluctuation for the picture reproduction of good color balance. The identification of the Vidicon's dark current is the first thing to do in the dark current compensation. How is the dark current actually identified? The Vidicon's faceplate is black masked, and the incident light rays are shut out by this part to make the optical black. The signal obtained by scanning this part is the dark current, and this is a level to be detected. Suppose this part is the Vidicon's scanning area. The signal obtained looks like this. This portion is the vertical blanking period, that is, the period that the Vidicon's beam cuts off. This portion is the signal that the incident light is shut out by the black mask, which means the level of the dark current. The way to detect the dark current behavior out of this signal is to sample gate this part with the gate pulse like this. The increase in dark current shifts the level toward the image signal, and the decrease shifts it toward the blanking. This figure is the block diagram of the dark current compensation circuit. The signal from the preamplifier is processed in the preprocessor and goes to the luminance signal processor and the color signal processor, respectively. The Y signal, the lower frequency component, takes care of the dark current detection. The input wave pattern of this dark current compensator takes the shape like this, and the increase in dark current pushes down its level like this. The gate pulse of this timing is added to the dark current detector. Only when the gate pulse is positive, the dark current detector is on and the dark current is gated in to be sample held the voltage like this by C213. This sample held voltage is guided to the non-inverting input of the operational amplifier and is comparison amplified to the standard voltage on its inverting input. In this case, the operational amplifier acts as a DC amplifier. The output voltage of the operational amplifier is negatively fed back to the clamper as a clamp voltage. The dark current compensator is to keep the black level constant by controlling this clamp voltage according to the dark current fluctuation. For example, when the dark current increases, with the temperature rise, the X221 input image signal optical black level shifts towards the white level, and the level goes down. Accordingly, the sample held voltage also goes down like this. This is compared with the standard voltage of the operational amplifier and is amplified so that the operational amplifier decreases its output by what the dark current increases. For this, the clamp voltage goes down, and so does the DC reproduction level of the color multiplex signal like this. Therefore, the upward black level is pushed down to be constant. In other words, the dark current fluctuation is cancelled. This is it about the principle of the dark current compensator. Burning compensator. In here, burning means the faceplate damaged by light, but not yet being destroyed. When this happens, we find the black level difference between the black masked part and the unmasked part on the oscilloscope, even with the iris closed. In order to achieve the right dark current correction, these levels must be equal. The burning compensator takes care of this job. This figure shows the operation principle of the burning compensator. The gate pulse cut out and adjusted by the burning compensation potentiometer is given to the X208 emitter. The color multiplex signal is put into the X208 base. The gate pulse input to the emitter during the 5H blank mask scanning period acts as a reverse bias for X208. Consequently, the X208 action current reduces during the gate pulse period so that the optical black level equalizes to the video black level. The burning compensator works to equalize the optical and the video black levels before the black level detector. So the burning compensation potentiometer should be adjusted to make both levels equal with the incident light shut out. Peak compressor. This is to compress the input signal slopingly like this, to get a better looking picture on the picture tube of the narrower contrast reproduction range. The peak compressor acts as a gamma compensator at the same time. Here is the peak compressor's block diagram. The circuit consists of a group of differential amplifiers from X206 through X212. The parallel tramps T204 and T205 get rid of the 4.1 MHz fundamental and the 8.2 MHz second higher harmonic from the original color multiplex signal, with the result being only the lower component of it. This makes the peak compressor's control signal and is applied to the compressor through the R216 gamma set potentiometer. This figure shows the basic operation of the peak compressor. The multiplex signal is applied to the X208 base and made an output through X207. X206 and X207 makes up a differential amplifier so that the sum of the current I2 of X206 and I3 of the X207 remains always I1. I1 is the current through X208 made by the input voltage EI. The peak compensation is done by changing the rate of current distribution in its differential amplifier according to the control signal. As is discussed, this control signal is the remainder of the multiplex signal with its fundamental and the second higher harmonic taken out. When the camera shoots the object with the characteristic that the incident light at the beginning of the scan is a little bit and gradually increases its amount, then the slanting wave pattern like this is seen. The picture image appears negatively in the wave. The stronger incident light makes the bigger video level. It makes the bigger peak compression control signal negatively. And this control signal pushes down the X207 base voltage. On the other hand, the X206 base voltage always remains constant. So the control signal determines the current distribution between I2 and I3, and it is understood that as the control signal swings toward negative, the current I3 decreases. As a result, the gains of X208 and X207, which are the signal pathway, decrease as the control signal increases. That is, even though the input signal increases linearly, the output color multiplex signal is compressed slopingly like this. The degree of compression depends on the magnitude of the peak compression control signal going back to X207. And the potentiometer to be adjusted here is called the gamma set potentiometer. In the real-life adjustment procedure, this gamma set potentiometer is used for the luminance signal gamma adjustment. The gamma balance potentiometer is in charge of the gain of X208 and X207 as a whole by adjusting the current distribution of X206 and X207 DC-wise between the two. In actual procedure, it is used to adjust the Y-set signal level. AGC automatic gain control. The AGC has a role to raise the camera's sensitivity under the insufficient light source situation. The figure shows the AGC block diagram. The luminance signal passes the peak compressor, the F1 and F2 traps, the delay line, and goes out of the aperture compensator. The AGC's control signal is taken out from the emitter of the aperture compensator. This way, the image picture appears in negative polarity. This signal is applied to the operational amplifier's reverse input. The mean level of the signal is detected and amplified. The operational amplifier works as an integrator. To control the AGC, it outputs DC voltage according to the mean value of the luminance signal, comparing to the standard voltage applied to the reverse input. Here, the basic AGC operation is indicated in the figure. Similar to the peak compressor, as you've seen, the operation is carried out by controlling the current distribution in the differential amplifier X213 and X214 DC-wise. For example, think about the case that the object's illuminance becomes small to reduce the image signal in this way. Its mean level becomes higher during the blanking period when it's clamped at the specified level. This signal of the mean level is processed by the operational amplifier with its output being this small. Therefore, the X214 base voltage reduces with I3 going down and I2 going up. The upshot is that the smaller the output signal makes with the illuminance decrease, the bigger the sensitivity becomes with the gain of X207 and X213 boosted. The AGC does not start working until the auto iris is released. The circuit also works as an AGC canceller. Let's think about the operation when the object's average illumination gets higher and the auto iris starts closing gradually from the released position. The operational amplifier's output voltage gets high enough to make X214 on and X213 off. In this case, its AC load resistance becomes 1 kilo ohm of R222, that is, its total load resistance becomes 1/2, with its comparative gain being negative 6 decibels. On the other hand, under the low illuminance situation, X214 is turned off and X213 turned on, and its AC load resistance makes the sum of R221 and R222, that is, 2.4 kilo ohms, with its sensitivity increased by positive 6 decibels. The AGC balance potentiometer VR2 is to adjust the X213 base bias and determines the object's illuminance that the AGC starts operating to increase the sensitivity. In practice, we adjust it not to make the AGC work until the auto iris is released. The JVC camera employs the double equilibrium type differential amplifier to make sure to avoid the DC fluctuation. But the basic principle is just the same as we've seen. As a summary of what we've learned about the preprocessor, let's follow the signal flow on the actual circuit diagram. Here we have its circuit diagram. This part represents the peak compressor. The color multiplex signal enters the X208 and exits from X207. The peak processor's control signal that T204 and T205 make by getting rid of 4.1 MHz fundamental and 8.2 MHz second higher harmonic passes the R216 gamma set potentiometer and X209 buffer and enters the X207 base to do the peak compression. This part is the AGC. The signal from the peak compressor is admitted to the common emitter of X213 and X214 and departs from the X213 collector. The AGC control signal is obtained by integrating the luminance signal after passing the delay line by detecting its mean value. This is applied to the X214 base to operate the AGC. This part is the dark current compensator. X221 is the dark current detection transistor, whose base the gate pulse is applied to. When the gate pulse is positive, X221 is turned on to let the dark current in to hold its level in C213. This is comparison amplified by IC201 to make the clamp voltage for the dark current compensation. T203 in here is the pulse corrector for the correct color separation by adjusting the comparative phases of the fundamental and the second higher harmonic. The multiplex signal from the preamplifier takes the signal processing as such and goes through the X218 buffer to be divided into the luminance and the color signals. Now, stop the video recorder and do quiz 1 on page 4 and 5 and quiz 2 on page 14 through 17. Luminance signal processor. Here is the luminance signal processor's block diagram. This whole circuit is to eliminate the higher frequency component of the signal sufficiently enough with the traps T204, T205, and T207. Also, it does the job to delay the luminance signal by the delay line to correct the time difference of the color and the luminance signal in the whole system from the preamplifier through the NTSC output end. Also to compensate the resolution deterioration as by the optical frequency component erasing filter, the aperture compensation to enhance the apparent resolution is done. Then, it is to determine the blanking and the setup levels of the luminance signal and to make an output for the encoder. These are the roles of the luminance processor. The diagram here shows the blanking signal addition and the setup level adjustment circuits. The image signal enters the X225 base to be amplified and reversed on its collector side. The result is this wave pattern. On the other hand, the X225 collector receives the blanking pulse through D201. At the X225 collector, this wave pattern of the sum of the image signal and the blanking pulse is seen. X226 is a B-class amplifier which operates as an amplifier only when the emitter voltage exceeds the base voltage. Therefore, signal's blanking portion is clipped and shaped like this. The Y setup potentiometer is to change the X226 base voltage to result in the change of the clip level. Therefore, it can determine the setup level. The figure shown is the actual luminance signal processor circuit. The luminance signal is taken out from the preprocessor by way of T204, 205, and DL201. The luminance signal gets the aperture compensation for the better resolution at X222 and is sent through the white clipper X223 and X224. Then it mixes with blanking pulse at the X225 collector through D201. X226 is the B-class amplifier. The R255Y setup potentiometer is adjusted to change the clip level, that is to say, to determine the setup level. After all done, it is ready to go to the encoder through the X227 buffer. Color demodulator. The color demodulator is made up of a R and B separationer and a synchronous detector. The figure is showing the principle of the R and B separationer. The multiplex signal taken peak compression, AGC, and phase compensation in the pre-process amplifier goes through the further compensation for the better peak-white balance and into the R and B separationer. The 4.1 MHz and 8.2 MHz BPTs, bandpass transformers, take the color carrier waves. That is, 4.1 MHz fundamental and 8.2 MHz second higher harmonic out of the color multiplex signal. Then, this 4.1 MHz wave is conducted to the adder and the subtractor. On the other hand, the 8.2 MHz second higher harmonic gets a sufficient amplitude limitation from the limiter before going to the multiplier. The multiplier executes the multiplication between the sufficiently amplitude limitation taken 8.2 MHz second higher harmonic and the 4.1 MHz fundamental. And here, the second higher harmonic gets the amplitude modulation by the fundamental as well as the frequency conversion into 4.1 MHz. This frequency converted 4.1 MHz is similar in amplitude to the fundamental and differs in phase according to color. If the sum of this multiplier's output signal and the fundamental is obtained, it makes the blue amplification modulated wave. And the difference of these makes the red AM wave. The figure shows the R and B separators principle in terms of wave pattern. Here, S7 represents the multiplier's output signal. That is, the new signal which the second higher harmonic is converted to in the same frequency as the 4.1 MHz fundamental. When the camera is shooting a white or magenta object, the S7 wave is of the same amplitude as the fundamental, but its phase proceeds by 90 degrees from the fundamental. When shooting a blue or cyan object, S7 is the same both in phase and amplitude as the fundamental S2. In the case of a red or yellow object, S7 differs in phase by 180 degrees from the fundamental S2. In this way, the new signal converted into 4.1 MHz is similar in amplitude to the fundamental and different in the phase according to the color. The sum and the difference between the original 4.1 MHz and the new 4.1 MHz will do for the R and B separation. When shooting at red or yellow, the phase difference between S2 and S7 is 180 degrees. If added together, the sum makes 0, and the subtracted difference makes the double-sized signal. The subtractor's output is therefore the red AM wave, and the other's output 0. When shooting a blue or cyan object, S2 and S7 are the same in phase, so the sum of these makes a double-sized signal and the difference makes 0. In this case, other's output gives the blue AM wave and the subtractor's 0. When shooting white, S7 is forwarded in phase by 90 degrees, so neither the sum nor the difference makes 0, and the sum gives the blue AM wave, the difference the R AM wave. As we've seen in the R and B color separation of JVC GXV7, the amplitude information is obtained only from the fundamental wave, and the second higher harmonic gives minimal information about phase determination. This is it for the principle of the R and B separation. Let's look at the adder and subtractor of the R and B separator. The added circuit looks like this. The original fundamental is given to the X238 base, and the new frequency converted 4.1 MHz to the X230 base. To obtain the sum signal, there sits a 4.1 MHz transformer on the pathway of the I1 and I2 composite current. To take out the difference, there put another 4.1 MHz transformer in between the both emitters. This is what is done to separate R and B. At this stage, there are in the 4.1 MHz carrier wave. The following synchronous detectors detect these to pick up the R and B primary color image signals. Here is the actual circuit of the R and B detector. The fundamental component is extracted by the T208 4.1 MHz bandpass transformer and goes through C224, R298, IC202 number 10 pin, and Q23. It is at last applied to the bases of Q20 and Q21. It is also applied to the base of the other subtractor X238. On the other hand, the second higher harmonic is picked up by the T209 8.2 MHz bandpass transformer and conducted to the number 14 of the IC202. Then, the limiters Q1 through Q12 give it sufficient frequency limitation, and it goes through the Q13, Q14 buffers and reaches the basis of the Q18 and Q19 switching transistors. This group of differential amplifiers, Q17, 18, 19, 20, 21, 22, and 25, execute the multiplication between 8.2 MHz and 4.1 MHz and give the output of new 4.1 MHz signal. This new 4.1 MHz signal is conducted to the base of the X230 other subtractor. X230, X238, T210, and T211 make up a other subtractor. T210 gives the difference between the new 4.1 MHz and the original 4.1 MHz fundamental, that is, the separated red AM wave. T211 gives the sum of these two, that is, the separated blue AM wave. Synchronous detector. The detector is the mechanism to pick up the original R and B primary color signals by detecting each of the separated R and B AM waves from the R and B separator. JVC GXV7 employs the synchronous detector for its linearity and for its consideration for the power supply's regulation. This figure illustrates the operation of the synchronous detector. First of all, the input AM wave obtains the limiting sufficiently. This limiter's output is given to the Q10 base. By turning Q10 on and off, the AM wave applied to Q17 is detected. After passing the low-pass filter, the primary color image signal is obtained. Here is the actual circuit diagram of the blue signal synchronous detector. The blue AM wave from T to 11 is conducted to number 7 of IC 204. The signal from the pin number 7 goes through the buffer and amplified by the differential amplifier Q15 and Q16. But on the corrector side, the diodes D1 and D2 are inserted to limit the signal into the rectangular signal. From the Q15 and Q16 corrector sides, the rectangular waves of the reverse polarity to each other are obtained. These are applied to the bases of Q13 and Q9 through the buffer Q12, and also to the bases of Q10 and Q14 through the Q11 buffer on and off by turns. The Q8 buffer output is also amplified to the base of Q17 and boosted by Q17 and Q18, then detected by Q10 and Q13's on and off operation. The detected output is given at the pin number 5, and the blue primary color image signal is obtained by letting the output pass the T212 low-pass filter. Please stop the video recorder and do quiz 3 on page 24 and 25 of the training guide.